and then I will click on recording. Okay. Fine. And then I will disappear and I will leave you.
Okay, good luck.
Thank you.
See you.
See you.
See you.
Okay, 1 minute, we should doubtlessly be started.
Right.
No, not unmute.
Okay, 2:30. I should like to welcome everybody. We shall get started with this afternoon plenary session, which is the EPS-CMD Europhysics prize session. So my name is Kees van der Beek. I am the chairperson of the Condensed Matter Division of the European Physical Society. So I will chair this session. We will start. So the EPS Condensed Matter Division Europhysics Prize for Outstanding Achievements in Condensed Matter Physics has been presented annually since 1975 and biannually since 2006. It is now one of the, if not the most prestigious award for condensed matter physics that is given in Europe. The EPS-CMD Europhysics Prize is awarded in recognition of prominent and well-identifiable discovery, breakthrough, or contribution in condensed matter physics by one or more individuals, and the contribution that, in the opinion of the selection committee for the prize, 6 previous prize winners, represents scientific excellence. And this award may be given for pure or applied research at the discretion of the society. So EPS-CMD is extremely pleased to say that in the 2020 edition, we had a record number of 20 nominations, all extremely strong, which expresses the vivid interest of the community in the CMD Europhysics Prize. The EPS-CMD Europhysics Prize is endowed with a diploma and a cash award and the invitation of the laureates or laureates to present the prize lecture at the General Conference of the Condensed Matter Division of the EPS. And that's why we are here together today. The prize is sponsored, currently sponsored by the EPS, as well as by EPL, ex-Europhysics Letters, which is the EPS's and Europe's flagship letters journal. And before we continue, I would like to hand the floor to Bart van Tichelen, who is the editor-in-chief of EPL, who will say a few words about the journal.
Yes, thank you. Thank you, Kees, for this very nice introduction. First of all, I would like to thank the organizers to set up this very interesting meeting on condensed matter physics, and in particular their successful efforts to change this into a virtual meeting on such a short notice. Everything seems to be possible today. Yesterday, I attended the session on Casimir physics, and even a virtual group photo was taken. Of course, I want to congratulate Professor Jörg Wrachtrup for his successful work on the physics of spins that is today rewarded by the prestigious Europhysics Prize. This prize is attributed by the European Physical Society and awarded by its president in a few minutes. What I like to mention is that this prize is for a great deal supported by the EPL, the ex-European Physics Letters. This journal, as you know, is our journal, published under the auspice of the European Physical Societies, by publishers owned by physical societies. I think it is very important, and I want to insist on that physical societies stay actively involved in the publishing process, as they have been doing for more than 1 century. One of the many advantages is that the profits they make, which for EPL are modest but by far non-negligible, can be re-injected back into the community of researchers. It is from these profits, for example, that EPL supports this Europhysics Prize. EPL supports other events as well, for instance, in relation to the EPS Young Minds or concerning national gatherings of different physical societies and events in Europe. A great danger in this modern world, I think, is what I call the prestige problem, the increasing tendency to publish in journals with high impact factors. This has become a real business, and they are not always controlled by learned societies. Please remember that EPL is our journal, is your journal. It is controlled by the European Physical Society, as well as almost 20 other physical societies in Europe. Do not hesitate to submit your work to us as a young mind, or even as a prestigious award winner of the Europhysics Prize. Thank you very much.
Thank you very much, Bart. So now it is up to me. It is my very great pleasure to announce the 2020 CMD Europhysics Prize winner. So the prize this year is awarded to Professor Jörg Wrachtrup of Stuttgart University in Germany for his pioneering studies on quantum coherence in solid-state systems, their applications to sensing, in particular major breakthroughs in the study of the optical and spin properties of nitrogen vacancy centers in diamonds. So I would like to give Professor Wrachtrup an enthusiastic hand, which is bizarre online, but my most sincere congratulations. I shall now say a few words about your curriculum. So Professor Jörg Wrachtrup is one of the pioneers of solid-state quantum physics. He received his PhD from the Free University Berlin in 1994. And at that time, he already did the first ESR electron spin resonance experiment on single electron spins in matter. He then went on to a research position as lecturer in Chemnitz at the University of Technology, where for the first time you detected optical as well as the spin signal from single dopant atoms in a diamond, which was the discovery of the NV center in diamond. And you have contributed tremendously to the understanding of the material science and the physics around this and other defects in solids. Since 2000, Jörg Wrachtrup is professor in physics and director of the Third Physikalisches Institute at the University of Stuttgart. He was appointed fellow of the Max Planck Institute of Solid-State Research in Stuttgart in 2010, member of the Berlin-Brandenburg Academy of Sciences in 2018, and he is now director of the Center of Applied Quantum Technologies. The research of Professor Jörg Wrachtrup has established an entirely new and highly successful area of research at the interface between solid-state physics and quantum optics. This has an unexpected impact in quantum sensing, from material science to biomedical research. And all this is based on his pioneering work on the optical detection of single spins in solids. This has spurred considerable development of ultra-pure diamond as a material, diamond nanostructuring technology, as well as solid-state nanotechnology as a whole. Jörg Wrachtrop's research has prompted the systematic invention of many other solid-state spin systems in many other materials, wide gap semiconductors and insulators. So it is now my task to invite the EPS president, Petra Rudolph, to symbolically hand over the CMD Europhysics Prize to Jörg Wrachtrup and to be the first to congratulate him.
Yes, so normally if we were able to meet in person, Kees would at this point hand me the diploma, which he has now in his hands, and I would be able to hand it over to you. But unfortunately, we will have to send it to you. That does not mean that I'm not very, very happy to congratulate you on this prize on behalf of the European Physical Society and on behalf of the 130,000 European physicists that we represent. Thank you very much for all the work you have done, which is recognized today.
Okay.
So get a photo now.
I virtually stretch out my hand and take the diploma. Thank you.
Congratulations. Let me, in my turn, extend my warmest congratulations for this fabulous work. Congratulations. So now there is a group photo.
Mm-hmm.
So our Spanish colleagues will confirm whether the four of us are in it. So I am waiting for confirmation that the snapshot has been taken. Jose Maria?
I think you can continue.
Yeah. Thank you very much. So with this, I would like to invite Jörg Wrachtrup to take the floor and deliver the prize lecture. Thank you.
Thank you very much, Petra, Bart, and Kees for your warm words, and thank you also the whole EPS and the EPL actually for endowing this prize. It certainly means a lot to physicists across Europe to have such a prize, and I sincerely believe it generates coherence across physicists in Europe and strengthens our mutual communication and collaboration. I would also specifically like Bart and Kees for the exquisite pronunciation of my last name, which is a tongue breaker to most people, but I was born close to the Netherlandish border, and so it probably has an edge, you know, of Netherlandish with it. Yeah, and Petra, once again, also thank you for essentially sharing this prize ceremony and also for all the work you put into the European Physical Society. And I think, of course, the selection committee for having selected me. I can tell you it came as a surprise, but I'm nevertheless grateful, of course, to be among the large number of fantastic scientists who have been recipient of this prize. All right, so now let me, I prepared something like a 35 minute presentation of the science we are doing. And let me try to share my screen. Okay. All right, that seems to work. So I was promising you a short excursion through our work, and this is our attempt to actually engineer or assemble quantum systems atom by atom, and a picture from the lab which actually shows what this means. You see here on the right side, and I'm going to explain you actually what you see here in the course of my talk. All right, so what is actually the research we are doing, and actually a growing number of people in our community, which I think is fair to say is a sub-branch and a growing sub-branch in condensed matter physics, are doing over the past, say, 10, 15 years. What we are doing has taken or has developed into a quite amazing, large number of different applications and different research directions. Starting with quantum information processing, and I'm going to explain you a bit what we are doing in this science. But it's also good for biomedical analytics. I will give you a short glimpse in actually what this is about. Quantum sensing using these using our quantum systems we have is a big topic, and I'm also giving you a flavor on what we are doing in terms of quantum sensing for, in this case, magnetic materials. But it also now becomes a subject in the industry. There is a growing number of companies trying to use the sensors we use in basic science for product development. And one of the early attempts where actually industry was using our sensors was in the development of hard disk drives, or to be more specific, in the development of write head for hard disk drives, which are getting smaller and smaller these days, right? Their dimensions are getting significantly below 100 nanometer. And at these dimensions, you need new sensors actually to measure the field profile emanating from this hard disk drive write heads. And this is what a couple of companies are doing these days to perfect their products. All right, so what is actually the solids we are working with? And typically, the solid state materials we have in our hands and we modify are wide bandgap semiconductors or insulators. And what we do, and you in his audition, Bart was already referring to that, is we dope these materials, essentially generating isolated energy levels in the bandgap. And we do it in such a way that these dopants do show strong optical transitions. This is why they typically are called color centers, because if you have high doping densities, then they give a particular color to the solid you are working with. So these optical transitions typically are in the electron volt range. And we specifically work with systems, with dopants, which do have a spin, which normally is an electron spin, say 1 or 2 or 3 unpaired electron spins. What we then do is we use these optical transition as a means to address these dopants, right? So they are, we use doping levels where we can optically isolate single of those dopants, impurity atoms, like nitrogen in diamond, or vacancies in silicon carbide, and so on and so forth, or rare earth atoms in different solid state materials. So we address individual of those atoms in the solid, and we seek to have as low readout noise as possible, which actually is quite easy with optics. It is sometimes much more hard if you have electronics, that is, if you have an electrical readout, which sometimes you can also do instead. But once again, the optics is only for addressing and reading out what is happening with the spin. So the spin levels or the spin sublevels actually are the quantum levels we work with. They provide a means of long coherence time, and long in our case means seconds or so. And they also allow for very precise coherent control. That is, we can coherently control the quantum state of that spin with exquisite sensitivity. Just to give you an idea, maybe on the kind of precision we reach here, later on in my talk, we will talk about sensitivities. And in the systems we are working with, we actually can measure the spin splitting between these two spin sublevels, right? -1/2 and +1/2 would be, say, a spin pointing towards along a magnetic field and anti-parallel to a magnetic field. So we can measure the Zeeman levels here with a sensitivity of a few hertz, which essentially are a few femtoelectron volts. And we do this on top of a signal which has electron volt energy. right? So this delta E over E of 10 to the minus 15 is actually what we are living on in these systems. Now, what are the solids we are doing this with? So historically, the first experiments we did in diamond, that's what you see here on the left side, where we dope actually nitrogen into the material. I'm coming to this later, and this gives you these isolated spots, and the spots you see here actually is photoluminescence. It's spatially resolved photoluminescence of individual impurities in diamond. So we also work with rare earth ions. Rare earth ions are well-known candidates in optical communication technology. For example, fiber amplifiers are use these ions. Lasers use these ions, and we can also dope them in dope atoms like cerium, praseodymium, or europium into different hosts, like yttrium aluminum garnet, yttrium silicate, and so on and so forth, and see individual atoms. Since a couple of years, we work with silicon carbide, which is a material which is well known in the semiconductor industry for high power electronics. And it turns out that this is also a very good material to look at individual atoms and do quantum physics with it. And here, these spots you see here actually are single holes, single silicon vacancies, and it's a photoluminescence of that material. And a few years back, like 2 years back, we were also having our first successful measurements on single spins in 2D materials, specifically in boron nitride. And this is something we have lots of fun with in the past couple of years. All right, but for simplicity, and because I mostly will talk about the quantum physical use of these defects, I'm focusing myself here on the diamond system. Okay, so let's get a bit more specific how such a prototype impurity system looks like. So diamond, as you know, is made up out of carbon, right? Carbon sp3 bonded to its nearest neighbors. It has a band gap of around 5.5 electron volts, so it's really an insulator. It is transparent to optical irradiation. That's very important because we address and read out impurities optically, as I was mentioning already. When you dope diamond with nitrogen, and when there is a vacancy, a hole next to it, this you can achieve by actually tempering the material. Then you get these isolated levels here in the band gap of diamond at an absorption energy of around 2 electron volts, right? So that's well isolated from the conduction and valence band of the material. And then this excited state decays by emitting light, photoluminescence or fluorescence. And what you see here on the picture, this spot here is nothing but the photoluminescence of a single of these dopants or impurities here by a micro PL, right? So it's an optical microscope actually capturing that light. And of course, the size here is given by the diffraction limit of your imaging optics. That is a room temperature experiment. A diamond is such a good host in our terms, and I'm coming to that, what that means, that you can do lots of the experiments without cryogenic cooling. Now, the system here, there is more than 500 different of these color centers known in diamond. And we specifically work with this dopant here because it has this ground state spin structure. It's an electron paramagnetic ground state system. In the case of this system, the total spin S is 1. So you have 2 electrons which are unpaired and which are coupled by exchange interaction. And if you put that in a magnetic field, right, then you have MS can be +1, -1, or M sub S can be 0, which is a which is a spin state which has no magnetic moment. And now if you irradiate electromagnetic waves at the right frequency, which is typically depending on the field you have in the gigahertz range, you can induce magnetic dipole transitions, right? These are spin sublevels, so this is a allowed magnetic dipole transition. And if you then use the fluorescence as a measure, as the observable in your experiment, and you change the microwave frequency, then depending on the field you are choosing, you come here into resonance, and what then happens is that the fluorescence drops, and it drops because it's mostly the M sub S0 level, which is taking part in the optical excitation and emission process. So if you look at the fluorescence as a function of microwave frequency, you come into resonance, and this marks this transition. Now, it is very easy now, not only to, have a pumping or a classical transition being generated by the microwaves, but you can also generate oscillations, quantum oscillations between these two sublevels. So once again, fluorescence intensity as a function now of the time you apply the microwave field, and you see these characteristic oscillations, and they indicate quantum coherence between these two levels. And it is one of the characteristics of the systems we are choosing, we are selecting of the whole wealth of solid state systems, that you can follow these oscillations for many milliseconds, if not seconds, right? The time scale here is microseconds. And typically, if you look at the decay of this amplitude as a function of time, then it looks something like this, right? So this is now the envelope function of this oscillation, and see now this is once again microseconds, but it's thousands of microseconds. So the decoherence time, that's what we are measuring here, is on the order of milliseconds under ambient conditions of this single electron spin. And this is because diamond on the one hand has a large Debye temperature, 2000 K, which essentially means that there are no optical phonons being excited even at room temperature, and diamond is made up out of carbon, so it's a light-weighted material. You have low spin orbit coupling, and just to compare this to other materials, so we have a T1 time, spin relaxation time of some milliseconds. In gallium arsenide, for example, the same time would be like 10 to 100 microseconds at 2 Kelvin. And at room temperature, it's below a nanosecond. And the same is true for dopants in silicon, for example. Phosphorus in silicon has the same kind of numbers here, very fast relaxation. Having these long times simply tell you that you can coherently control these spins for a very, very long time. And this is what we make use of. And another important ingredient is that your host material does not contain too many spins, specifically nuclear spins, which generate a random magnetic field which dephase your electron spins. So you better choose materials which have a low abundancy of nuclear spin isotopes. And carbon has only 1% of carbon-13, which carries a nuclear spin. All right. I was promising engineering now these systems atom by atom. And this is what we envision. Rather than having a single defect center, right, which would be one of these arrows here, we were working, and we are still working towards making larger arrays of these electron spins in diamond and silicon carbide and other materials in a regular array type of fashion. And we want to have it, and we want to have these electron spins as close as possible together at distances which are maximum on the order of some tens of nanometer. And this length scale is actually given by the fact that we want to have these electron spins interacting by magnetic dipole interaction. So we don't want to have exchange interaction coming into play. So angstrom scales or so is not what we are interested in. but we want to have a strong magnetic dipole interaction, because this magnetic dipole interaction is what we use to generate larger coherent clusters, larger coherent states across this cluster of electron spins. At the same time, we want to have single site readout, which is possible because clever people like Stefan Hell, Nobel Prize recipient, were inventing optical super resolution techniques where you can actually address individual of those spots with a spatial resolution of 20 nanometer per optical means. And then we want to control these spins. So that's the kind of was the research agenda here in our lab for a long time, and still is. And how does this look like in practice? So the way we generate these regular arrays of closely spaced spins is that we shoot the impurities we work with into the solid, and we do this through nano apertures. So this is an array of apertures with nano-sized holes, 20 nanometers or so sized holes, and then the lattice constants here is supposed to be 50 nanometer or less. And it's for most hosts, and this is true also for diamond, you need some kinetic energy to put impurities like nitrogen in. And the kinetic energy is a few kilo electron volts, so you need to have actually a single ion gun with that energy. And we are working together with people from the ion trap community, like Ferdinand Schmidt-Kahler from Mainz, and he's really an artist in this. So he's trapping individual of these atoms in an ion trap, right? And then he's shooting that out of the ion trap into the material we want to have, in this case, diamond. And that's it, right? If you do this right, then you can make small quantum arrays out of it. And so the whole machinery around what I'm explaining here looks like this. So this is a typical, experimental table. You see, we have a strong background in optics. We need to have this for readout of our spins, and that's what you see here, right? Mirrors and fibers and so on and so forth. And inside here, this box, we have a small control chip. So what you see here actually are control lines for the individual spins, which are bonded then to the chip, in the center of which we have a small piece of diamond with these impurities in here. And what you see here, once again, that's a photoluminescence map. These red spots here mark the photoluminescence of individual of these NV centers. Well, this is an individual one, this is an individual one, and these are multiple ones. Length scale here is on the order of 0.1 micrometer. So, and then you go, right? Then you have your small quantum processor assembled. And what is it we are doing with it? So now I really very briefly describe you how we use now these individual spins and how we combine them to make specific quantum states, right? And for example, say we have this register here, and we want to make a quantum state which looks like this. So plus means that the spin is parallel to an external magnetic field, and minus means that it's antiparallel to an external magnetic field. And this is a two-particle correlated state where we have two spins which are either both pointing up or both pointing down with respect to an external magnetic field, right? And they are in a coherent superposition between these two states. And say we take these two impurities here, and then we have ways by microwave control to specifically make those states. I'm not going to explain you how we do this, but by coherent control of the individual spins and by the interaction, you can make these states. And typically what we do, or the result of a measurement then on these two spins here, looks like this. It's a graphical representation of a density matrix Just to walk you through why this is indicative that we really have made this state here is, so what you see here on these axes are the entries in the density matrix. And you see we have an entry here at plus and plus, right? So this indicates that we have population in the state where the two spins are up. And the same we have here with the minus state. So we have population, we have a probability to find the two spins being spin down. But we also have these off-diagonal elements here, plus, minus, and they indicate coherence, right? They just tell you that you not just have a statistical mixture of the spins being up or being down, but that you really have a coherent superposition of these two states. And you also see that all the other matrix elements are not zero. They have a small value, and as a result, also these bars here, which should be 0.5, are not 0.5, but a bit larger. So there is some compromise, some in the quality of those states. Now you can also take these two neighbors here and do the same game, right? It's the same result. If you look here once again at this representation, you see that it looks almost identical, except one point. The bars here are lower, significantly lower than here. And why is this so? It is so because the distance is larger. And so the interaction is smaller. And so it takes you longer time actually for the two spins to come into exactly that state. And the longer it takes, the more residual interaction with all the other spins here, but also with dirt you cannot control, come into play. So there is some limitation in the distance you can apply this kind of controlled generation of quantum states over. These are results we have taken a couple of years back on a similar system, not exactly this one. I'm cutting the story here short. Meanwhile, people have made progress, and there is a very active, very nice group from Tim Terminao in Delft, a colleague of Ronald Hansen, and he now has garnered control over more than 20 spins in this fashion. Then that's a Nature paper from last year, and this is what this field is about, right? So what you try to do is you try to have as many of these spins, that is qubits, coherently interacting as it gets, and this is about now the record number which is out there. If you want to have more, if you want to have larger arrays, then it is very hard to scale it with this technology, because the larger the number of spins, inevitably, the larger the distance is and the less good your quantum states are. And this is what we and others are trying to work on now. So what you do is, rather than using the magnetic dipole interaction among the spins for generating quantum states, you take a certain number of spins, like what I'm showing here in the middle, representing a cluster of these individual spins, and then you pack them up in an optical resonator. And this optical resonator functions in such a way that it generates a strong interaction between the photon being emitted by these defect centers, by the spins, the optical photons, and the spin state. And so from this point on, you don't use magnetic dipole interaction to communicate coherence, but you use the photons. And this you can scale up pretty easily. And this is what we and others are trying now. And this is, you see, now you have individual of these building blocks, which actually you can use photons to entangle a distant of these spin registers via the photons and the resonators they are using. And this is not science. The drawing is, of course, an artist's impression, but it's not entirely science fiction. So people have actually succeeded in having 2 of these registers being entangled by photons lately. And then we see how much we can compete with this with other technologies like superconducting qubits and so on and so forth. And after my talk, I'm happy to discuss on how actually the quality of these type of system compares with the competitors in the field. Okay, so for the rest of my talk, I would like to switch over to my second topic, which is quantum sensing. What you see here, this graph here shows, by the way, the viscous flow of electrons in graphene. Very nice recent paper from Ron Bolsworth and Ami Jacobi, in which they were using diamond and V centers actually to image the flow of electrons in graphene with very good spatial resolution and very good sensitivity. Before going to experiments like this, so I'm showing you 1 or 2 examples of experiments we were doing. Let me give you an overview of what type of quantum sensing you can do with these systems and how you do it also. So because of the long coherence time and our ability to read out the Zeeman splitting between these spin sublevels with such good energy resolution, we can measure actually the impact on the spin splitting, on the Zeeman splitting of the spins of magnetic fields, electric fields, temperature or force with very good sensitivity. So right, imagine you have a single electron spin, right, and you bring a magnetic field close to that electron spin. Of course, the spin up, spin down splitting will change, and this gives you a measure of the magnetic field, right? And because we have only a single spin, we can also gain spatial resolution. So you just use the Zeeman interaction as a means to measure a magnetic field. The systems I was saying are characterized by small spin-orbit coupling. But the spin-orbit coupling, because we have such a long coherence time, is still large enough to actually cause the magnetic spin sublevels to shift because of the presence of an electric field, right? This goes by spin-orbit coupling. And by this, you can measure actually electric fields also with these defect centers. And for example, we use this to measure the electric field across these flash memory cells, right? Which obviously is of importance for electronic industry. At the same time, you can also measure temperature and force. And the reason is that when you heat up your diamond, then the lattice constant changes. And because you have 2 electron spins, also the average distance between the 2 electron spins in your defect center will change. And this you can also measure by a shift in the Zeeman levels. So this essentially is kind of spin-phonon interaction. And then people are making hybrid systems to measure other quantities like pH, redox, or target chemicals. All right, I will, for brevity, I will just explain you what we are doing in terms of measuring magnetic fields. Probably one of the most delicate pieces of technology we have these days in the field are structures like this. So there are people who are able to fabricate scanning probe tips. Essentially, these are tips as you find them in an atomic force microscope out of diamond. So this this brownish piece here of matter is a diamond, which is on a holder. And then there is a small tip here, right? A small diamond tip. And at the end of the tip, this is something I added in PowerPoint, is a single defect, right? You can actually optically address the single defect through the diamond, through the back here of the diamond. So this is how you read out the spin signal here from your single defect. And then you can scan that across a surface you would like to have, right? And if you want to measure, then with that you can, for example, measure the local magnetic field. You can buy these chips these days. There is at least 2 companies I know of, both of them in Switzerland, and they sell it to you. You can put it into your apparatus. It's just a word of warning. These chips come at a Swiss price level, so you better make your student not breaking it. But they are good, and it works. They work pretty well. And now I'm showing you one application example of such a scanning magnetometer. And this comes from 2D magnetic systems. I mean, I probably don't need to say you that 2D materials, especially these van der Waals materials, are an enormously powerful material platform in all regards. And recently, they also have been discovered to show magnetic moment. Right, there are 2 papers here, like 3 years back, having shown magnetism in chromium I3 and chromium germanium telluride. Because these systems come as single 2D layers, of course, the overall magnetic moment they show is very small. So you need a very sensitive way of measuring the magnetic order in these systems. And what those groups were using, at least the group from Jiadongzhou in Seattle, University of Washington, was MOG, magneto-optical Kerr effect. There you apply a laser with a certain polarization, and because of the interaction of the light with the magnetic material, that polarization changes. And by this, you get a measure of the magnetization. And what they were measuring on single layers are hysteresis curves like this, right? So you have a magnetic field here, and you have this depolarization angle. And if you ramp up the field, you get the orange curve. And if you reduce the field, you get the green curve. And voila, you have this hysteresis curve. And that's a good indication that there is magnetism down to a single layer. 2 layers of this material order antiferromagnetically. 3 layers, once again, have a net magnetic moment. So this is how they were doing it in 2017. And now, I mean, this is a material almost ideal for this scanning probe magnetometry. And the first one actually to do this was Patrick, or to show that this works, was Patrick Maletinsky in Basel. And what last year, and we also do this, and I'm showing you our results. We don't work on any of these 2 materials you have seen before. What we work on chromium brom 3. Chromium brom 3 is expected to be ferromagnetically ordered, and if you have 2 layers, you expect them to be aligned. So have in total a ferromagnetic order between the 2 layers. And what we were investigating is our bilayers of the system. So here you see an AFM image, and well, if you scan across here, you see a 2 nanometer step, and this is how we conclude that we have bilayers. And then we take the diamond magnetometer, right? You have your defect here. It measures the local magnetic moment, and then you scan it across, and you get images of the magnetic order in this bilayer. And this is how it looks like. So this is now 2 chromium 3 layers. What we measure actually with these single NV sensors at the tip is the local magnetic field. And that's what you see here, right? So this is a local magnetic field map. This is a length scale, it's 1 micron. And what you see is that this bilayer has magnetic domains, right? And this also tells you that it makes sense to use a method which is able to locally measure magnetic fields. If you are interested in the magnetization, then you need to do a reconstruction. You need to actually conclude on the magnetic moment from the magnetic field, which is a thing in itself. I'm not going to the details of these measurements, but just to indicate you what we can do here is actually get a quantitative measurement on the magnetization we get, right? We have a single electron spin, so you get essentially a calibration-free way to measure local magnetic moments. And in this case, we measure, this is a histogram here of, the magnetic moments we measure, but we measure something like minus 28 unpaired electron spins per nanometer square. Theory says it should be 32 or so. So that's pretty close, and we'll see, you know, who is right, our measurements or the theory. All right, so once again, I'm happy to discuss with you later on how this compares to other methods like magnetic force microscopy or scanning squid, which is an interesting comparison in itself. What we were also interested in is looking actually at how the magnetic order melts. So if you change the temperature, then the question was, how does the magnetic moment or the magnetic, exactly, the magnetic moment or magnetization changes. And this is particularly interesting in 2D, because depending on if you have a 2D system which has an XYZ magnetic interaction or an XY magnetic interaction, or which has just one component in its magnetic moment to be important, you expect different phase transitions when you go through the Curie temperature. So this is Gosterit-Thouless case here, when you have an XY system, and if you have a preferentially aligned system with strong anisotropy, then you expect this more or less classical increase in magnetization. And it is very easy with our method to actually measure the temperature development of this magnetization. This is probably the wrong citation I give here, but anyway, what I plot here is a magnetic magnetization as a function of temperature. And you see, if you come below the Curie temperature, it increases. And if you look into the theory, you see that it is best fitted by a 2D magnetic interaction XXZ plus a Kitaev type of dynamics. Once again, I'm happy to discuss this later on. All right, so finally, the last 5 minutes or so, I would like to show you how to detect even weaker magnetic moments. Whenever you do quantum sensing, that's what we do here. People ask you, how sensitive can you measure, right? And to show how sensitive you can get, we also try to measure actually the magnetic moment of nuclei. Right, the magnetic moment of nuclei is a factor of 1,000 smaller than that of electron spins, and you have seen that at least the magnetic moment of a 2D layer of electron spins we can measure very well. So now question is, can you also measure small amounts of nuclear spins, although it's a factor of 1,000 less magnetic moment. And here you apply a trick actually to make this possible. If you put your nuclear spins into a magnetic field, they start to precess, right? And they precess because they have a magnetic moment and they have an angular momentum, right? And it's these two properties which make them not align just parallel to a magnetic field like a compass, but to precess like a quantum object. And the precession frequency is precisely known. It's the G factor of the nuclear spin times the magnetic field you apply. So if you, rather than measuring the DC magnetic field, if you measure the magnetic field at that Larmor frequency, actually you can get much more sensitive, especially if the Larmor frequency is at high frequencies where it's away from the 1/f noise. And this is something we can do. We can actually turn our single electron spin quantum sensor into a lock-in type of system. And you do this actually by inverting the electron spin exactly in registry with the oscillation of the magnetic field, right? It's like in a lock-in, you do a rectification type of technique, and that makes you actually sensitive enough to really look at tiny amounts of nuclear spins. And we and others were showing this already a couple of years. So what you do is you have your NV center, this is your diamond surface, you put a small drop of a liquid on top, and then you measure the magnetic moment, which is precessing exactly at the Larmor frequency of proton spins in this case, and here you see the signal, right? And if you replace protons by deuterons, the signal appears. And if you put back a liquid with protons, once again, you see once again a signal. So this is nothing but a nuclear magnetic resonance signal of, by the way, around 100 nuclear spins, okay, in a detection volume of a few cubic nanometer. Okay, so and people now have gone down to single nuclear spins by perfecting the technique. All right, so we are not so much interested in the details, but let's compare what we are doing to what is existing out there. I don't know if you have, yeah, I'm finished in a couple of minutes. So for sure you have a chemistry department or a biochemistry department in your institution. And if you visit your colleagues, you find machines like this, 2 stories high, 2 levels high, right? And these are modern NMR, nuclear magnetic resonance spectrometers, with a sensitivity which is on the order of 10 to the 15 nuclei or so. And these are sizable installations because to get more sensitive, you need higher magnetic fields, simply because your nuclei rotate faster and they generate larger signals, right? That's as if you take a bike and you have one of these old bikes with an inductor, right? When you go faster, your light bulbs get brighter, and that's exactly what is happening here. And the more higher the field is, the better your sensitivity is, but the more costs you have in the machine. These machines we easily beat by 13 orders of magnitude with a technique which is orders of magnitude cheaper and more easy to apply, right? And that's something probably the provost or so of your university likes to hear. There are other pluses and minuses in the technique, but and then for now, this is roughly the difference. So this really has the potential to revolutionize this type of system. Now, and finally, I don't know if you know this NMR. Probably you have never had experience with an NMR, but once in a while, especially the skiers among us or the sportsmen and women among us know these machines. These are nuclear magnetic resonance imaging machines, which are used to actually image soft tissue, right? They are good in imaging soft tissue because they are good in imaging water. And this is a video here. It unfortunately doesn't run over a Zoom, but these machines are so good these days that you can actually follow people singing, right, in these machines. That's a baritone, Michael Volle, singing one an opera from song from Richard Wagner. Anyway, so can we do something similar like this? And indeed we can. So we can convert our machine into an imaging machine. The way we do this is rather having a point detector, we have a CCD, but all the rest is very similar. And this is the result. So this is how such a setup looks like. And this is what we are doing rather than putting a whole person on our machine. We were just putting a single cell on top of the machine. We took, this is an optical image of such a cell. It's a HeLa cell, that's a cancer cell. This is like 10 microns here, scale bar. You can actually stain the cell membrane by a dye, and this is then such a typical fluorescence microscope image of a cell membrane. Or you can measure with our machine the nuclear magnetic resonance of the phosphorus here of the cell membrane, and that's what you see here. And I compare this with an historic MRI image. So this is one of the first magnetic resonance images which has been taken now like more than 40 years back. It looks very similar, right? It's in entirely different dimensions. So this is actually a crosscut through a human on the height of its belly. And this is like 0.5 meter or so. And then this is like 10 micrometers. Signal to noise is similar. and see what has come out of this, right, in the course of like 20, 30 years. And hopefully we also get very much better getting similarly detailed motion pictures of what's happening inside cells with this machine. All right, so with this, I'm at the end of the story. Thank you once again for your attention. The gist of what I'm saying is that this is a rather generally, applicable technique ranging from quantum computing down to nanoscale NMR, which is good in bio, and future needs to show actually how much of this really is getting out of our lab into the lab of people to apply it. All right. So finally, I thank all my group members. You also see them here as a background in my Zoom screen. We have collaborations with really people from all over the world, from China to Australia. We received money from lots of different sources. Up until the last US presidency, we were also getting a bit of money from the US that drained out a couple of years ago. And we also receive money from industry these days, which is really new. So once again, thank you for your attention, and thank you also for your patience. Thank you.
Thank you very much. So we'll give a warm virtual hand to Jörg Wrachtrup for this very interesting, beautiful talk. There is very little time left for questions, so I propose that we will not have a questions session, but in keeping with what is the usual thing at this conference, let's turn on our videos, and we can take a snapshot of the audience with the prize winner and everybody else. So let's see who you are. Is this working?
I think Jörg has to unshare his screen.
Yes. I can see you all now in 11 pages. So, so here we go.
So let's make a few photos.
Let's make a few photos,
pages,
yes.
Indeed.